All right, so today's story is about motion in two dimensions. And of course, it's only about the description of the motion. I'm not really thinking about what causes the motion yet. Just thinking about describing motion. And motion in two dimensions, these two dimensions could be anything. Could be, up and down, left and right, or it could be northeast, sort of type situation like this. And then maybe an object is moving, and then maybe it moves on a straight line in one direction and then it goes in another direction, or maybe it's curving, so it's going around in a circle, something like that. These are the kinds of stories that we're thinking about. Now at each point along the trajectory, this object, it has the kinematic variables that we've talked about before. So you can think about its position relative to some reference frame, right? So you think about its position, and then you think about the change in that position. So that's called the displacement. Or you can also think about at any point it has some direction of motion and it's moving with some velocity. So that's another kinematic variable that you think about. It also might have some sort of acceleration. It could be in the same direction of the velocity or opposite to it, or even at a different direction of the velocity altogether. So all of these things are situations that we're going to encounter. And in all of these situations, you're going to think about each one of these things as a vector that has a magnitude and a direction, or you can also think about its components. So you can think about the east component of the velocity. For example, if I take this velocity vector, I think about the east component of that velocity, or the south component in this case, because it's heading in this direction opposite to the north. So you can think about the south component of this velocity. Or if you think about the displacement, so let's say you started at point 1, you ended at point 2, and let's say, you did something along the way, but the displacement vector is always pointing from initial to final like that. So you can always think about it's the x component of the displacement and the y component of the displacement if this is the full displacement vector. So as you can see, every kinematic variable that we've thought about before, whether we've thought about displacement, we've thought about velocity, initial and final for some segment, we've thought about the acceleration during the segment, and we've thought about the time interval. These things are called vector quantities, these things with the arrows on top. So that means that for each one of them, you have x and y components, or east and north components, right? So let's say I have some x and y coordinate system in which I'm going to be describing these. Then that means that this one then would have an x and a y component. The initial velocity would also have initial velocity in the x, initial velocity in the y, and so on. Final velocity in the x, final velocity in the y, the acceleration in the x, and the acceleration in the y. And the x and the y are coordinate system, basically a coordinate system that you choose depending on the kind of problem that you're playing with. The time, of course, is the same in x and y because the time is just the time between the two events. This is the time interval, and it's a scalar quantity, so that means it has no direction. That's why it has no components that I can think of. Now, the interesting part in this whole section is that if you understand kinematics in 1D and you understand how to think about these components, then the x components are just motion in one dimension. That's the stuff that we've talked about before, right? And the y components also form the kinematic variables plus the time, of course. Everything, the time is independent whether you think about the x and the y or the y. So the time would be part of the problem. So at any case, what I'm really trying to say here is that motion in x happens whether or not motion in y happens. This is sort of a very, maybe not the best articulated way of saying it, but the point is that when objects are moving in two perpendicular directions, you can think about motion in one dimension independent of thinking about the motion in the other direction. So in a lot of the problems that we're going to be thinking about, we're going to be thinking about projectile motion. For example, if let's say you have anything like a ball, for example, and then this ball is launched, and let's say this is the vertical and the horizontal. So the horizontal we're going to call x, up and down we're going to call y. So this object is launched with some velocity at the beginning. So you can call this its initial position in the X, its initial position in the Y, and then it gets launched with some velocity at the beginning, and then it undergoes this parabolic trajectory, right? Because when you throw anything, it goes up like that, and then it comes back down. And throughout its trajectory, you can think about its velocity at any point in its trajectory. You can think about the beginning, you can think about here, you can think about here. The velocity is always parallel to the direction, or tangent, I should say, to that curve. So it's in the direction of motion always. That's the direction of the instantaneous velocity, always in the direction of motion. Now, the direction of the acceleration, though, because this is under the influence of gravity alone, so only acceleration of gravity matters. So its acceleration is going to be always down like that at every point during its motion. It doesn't matter if it's moving up or moving down, the acceleration is always down because it's being pulled down. As long as it's under the influence of gravity alone, then the acceleration would be down. And in fact, I know exactly how big this is, but we'll talk about that in a second. But the velocity changes. So that means that at every point, I can think about the X component of the velocity and the Y component of the velocity at any point along this trajectory. I can think about the X component and the Y component of the velocity. Okay. Now, because the acceleration is only in one direction, so that means I can always write the acceleration vector as in the X direction is equal to 0, because it has no extension along the X direction at all. So its X component would be 0. But its Y component in this case is pointing opposite to what I'm calling positive Y. So it gets a negative sign, right? As we've always done that with components. And in this case, it's actually equal to exactly negative of G. If you remember, G was the acceleration of gravity on the surface of Earth, and it was 9.8 meters per second squared. So the Y component of the velocity is negative the G. G itself is just a scalar quantity, and it's 9.8 meters per second squared. So the Y would be, the acceleration Y in this case would be the acceleration due to gravity, and it's pointing down. Now, I could have chosen my axes to be like this. This is my X and this is my Y, in which case this would be positive because it will be in the direction of this axis. Remember that the choice of axes is always up to you because that's the tool that you're using. There's nothing physical about that. But to avoid confusion, maybe fix it for yourself one time. Decide these are always going to be my convention, unless the problem is something like, you know, something that's sliding on the side of a slope or something like that. Then we'll see how to handle that. But in general, this is a good choice for projectile motion problems in particular. Now, what I meant by the fact that the X and the Y components of the problem can be solved separately is that I can think about the X component of this motion. So let's say I'm thinking about the segment from A here to B here. So that's the segment I'm thinking about, A to B. Now this segment has X components of the displacement, and that looks something like this. So this is the whole displacement from start to finish. So this would be the Y component of the displacement from here to here, and then from here to here would be the X component of the displacement. So the X in this case sometimes is also called the range, and it's the displacement in the X direction from the start to the finish. The initial component of the velocity, that's at the beginning here. So I think about my velocity vector at the beginning. That's the initial velocity. And it has some X component and some Y component. And notice that this angle here has nothing to do with the direction of the displacement at all, because this ball could have landed here, could have landed here, could have landed here. Depending on where it's landing, the displacement would be from start to finish. But the initial velocity is the same all the time. It's just in the initial direction of the motion, the direction you've thrown the object. That's really the direction of the initial velocity. So you think about the initial velocity as having X and Y components. You think about the final velocity, which is the velocity at point B. This object, by the time it lands at point B, just before it hits the ground, it's actually going in this direction. And we never think about the part where it actually hits the ground. We're just describing the motion before it hits the ground. The collisions part is coming later in the course. But you think about the velocity at point B as pointing in the direction tangential to the curve like that. It has an X component and it has a Y component. The X component is this component that I've written down here. That's the X component of the velocity at the end of the segment that I'm studying. And then the acceleration is the acceleration during the segment from here to here. And if you remember, for kinematics, we need the acceleration to be constant. So this is always going to be constant for us. If it's not, then I have to divide the segment into a bunch of segments. And then the time. So these are the x components of the kinematic variables. I could also think about the corresponding y components of these variables. So delta y, the initial velocity, the y component, the final velocity y component, the acceleration y component, and the time. Now the time interval is the time between events A and B, which is, maybe I'll call it launch the ball just before it hits the ground. These are two events. There's some time between the two events, and that time, whether I'm thinking about the x part of the motion or I'm thinking about the y part of the motion, that time is exactly the same. And this is what I mean by solving two one-dimensional kinematic problems, is that these 5 variables, you can solve one-dimensional kinematic problem. These 5 variables, you can solve one-dimension kinematic problem, and they're independent of each other. The only thing that is that is the same in both is the t's. Now, obviously, the variables themselves are related in some way, because the x component and the y component of the initial velocity together, they make the initial velocity vector. So like I've said before, say this is the initial velocity vector, this would be the x component of it, and this would be the y component of it. And these are related to each other because, for example, this x component, as we've seen in the vector part, you can find it by, if you know the magnitude and the direction, you can say it's v naught cosine theta. The y component, you can always say that it's the magnitude times sine theta. So these two components, yes, I'm using them separately when I'm solving the problems, but they're related to each other by the magnitude and the direction of the initial. Now, if I think about the final velocity, let's say I solved the problem and I found Vx and Vy independently, right? So I found the x component of the final velocity and the y component of the final velocity independently. And now I want to find the magnitude and the direction of the final velocity. Then I say the final velocity vector looks something like this. It has some x component and it has some y component. How do I find, if I know these two, how do I find this magnitude? Then I say the magnitude is equal to, by the Pythagorean theorem, the x component squared plus the y component squared. And that's always true. In fact, that's true at any point during the motion. It's not necessarily just the final point. Okay, I think let's see a problem, because if we see a problem, it might be easier to understand how we approach these things. So here's an example that you can watch in these two videos what the story is, but let me just tell you up front. The story is that a balloon is dropped from a car moving at a constant velocity, and we know that it's dropped from a particular height, and then we're going to want to calculate some kinematic things here. But first, let's just watch what the story is about. So look at the balloon and its motion from this particular perspective. See it again. So you can see that the balloon is falling. You know, if there was no splash of water in the background and so on, you wouldn't even tell that there's any kind of motion, right? Because the balloon stays in the same position relative to the hand at all times. Now let's see this from a different perspective here. Okay, we'll see it again. So see the trajectory. Now the balloon at all times is under the hand of that person, and that's what we see from this perspective. This is the video camera that was taking this shot on the left, is looking at it from the top like that. But you can see that the motion of the balloon does this sort of parabolic thing, right? That is the way you see all projectile motion, it has this parabolic effect to it. And that's because in the x direction, it's moving at a constant velocity. And in this case, it happens to be exactly the same as the velocity of the hand. And the clue is that seeing the balloon is just falling into the ground and the hand is following it on top of it. So they're moving with the same velocity because they're always at the same position as time passes by. So the car is moving at a constant velocity. The balloon is also moving at a constant velocity in the x direction, but it's accelerating in this vertical direction because it's being pulled down by gravity. So that means there is acceleration due to the force of gravity that is pulling it down. Okay, so this is what the problem is. this is how you would sort of visualize what's going on. And before we solve this problem, let's draw it and think about the segment of motion that we want to study and so on. So here's a view of what the motion looks like from 3 different views. Let's just look at the side view, and that's the one that you can see in the second video, right? Is this parabolic motion of the balloon from the moment it was dropped to the moment just before it hits the ground. Now, if you look at that from the top view, that's exactly what you see from the first video, except that it's just not moving horizontally. But if you just imagine what this motion is like from the horizontal perspective, it just looks like it's moving in a straight line with constant velocity. If you think about the motion from a vertical perspective, for example, if I'm standing behind the car and looking forward, then what I see is I just see the balloon dropping like this. So the vertical motion, which you see from the back view, and the horizontal motion, which you see from the top view, combine to give you this motion that you see from the side view. And that's exactly how we're going to solve this problem. We're going to think about the Y part of the motion, or the vertical part of the motion, independent from the X part of the motion. The only thing that is going is, in fact, the time it takes for this balloon from the moment it's dropped to the moment it hits the ground. So it's just like any kinematic problem, the way to solve 2D kinematic problems is that, first of all, you need to think about the segment that you're thinking about, the segment of motion that matters to you. And the segment of motion that matters depends on what you're looking for. So here, part A says, I want to find the time it takes for the balloon to hit the ground from the moment it was released. So to find the time interval from this moment to this moment, or from this moment to this moment, it's the same time interval, independent of which one you're looking at, which view you're looking at. So I want to calculate the time of this segment. So that's a good segment to study then. So I'm going to be studying the segment from the moment it's to the moment just before it hits the ground. So the segment to study, let's call this point A and call this point B. So the segment to study is from point A, which is the balloon just dropped. So I guess that's what I'm calling A. And what I'm calling B is the balloon just before it hits the ground. And that's the segment of the motion that I want to study. Now for this segment of the motion, think about X and Y components of the kinematic variables. So I can think about the X component of the displacement, which, if I want to think about it on this diagram, where would it be? The X component of the displacement. Where is the displacement? The displacement is from start to finish always. So here's my displacement vector. Where's the X component of that? Well, the X is the horizontal component, so that would be from here to here. That would be the X component. That's my delta X, which you can also see on the top view. It's from here to here. That's the X component. But that I don't know. Okay, what else can I think about in the X direction? I can think about the initial velocity, but only the X component of that. The final velocity, X component, the acceleration, the X direction, and the time interval. I can also think about the same variables, or I should say the analogous variables, in the Y direction or the vertical direction. The displacement, the initial velocity, the final velocity, the acceleration, and the time. And if you break it down like that for any 2D motion, independent of what you really are looking for, this is a very good step to do. Figuring out what segment you're studying, laying down the variables so that you can start thinking about which variables you have and which variables you're looking for. So first of all, before we think about what we're looking for, let's set up the story here. Suppose a balloon is dropped. Now, dropped is a key word that is useful to know. Dropped meaning that I'm not throwing it. So that means it doesn't have any Y component for the initial velocity. And we've seen that when we were talking about free fall. Dropping an object just means that its initial component of the Y velocity is 0. It doesn't have any component of the velocity at the beginning. That's if I'm dropping this pen like that, that means at the beginning it was not moving at all. So that dropped is really important. From a car moving at a constant velocity. So that was the velocity of the car. And obviously that's the horizontal part of the motion. And that's the velocity that the marker would have, or the balloon would have when you first drop it. When you first drop the balloon, because it was attached to your hand, which is attached to the car, then it had that initial velocity, the same as your velocity, the same as the car's velocity. But as soon as you drop it, it's now independent. It's having its own independent motion, independent of you. But its initial velocity is the same as the car. So I could label that here. I could say that at the beginning, its velocity was in this direction, and it was the same as the car. It was 6 meters per second, completely horizontal, because I did not throw it downwards. If I threw it downwards, then it would also have some component to the motion that is down like that. But in this case, because it was dropped, then that component to the motion, or in other words, the y component of the initial velocity is equal to 0. And the balloon is dropped from a height of 0.8 meters above the ground. So I know that this is 0.8 meters here, from here to here. Where's the ground? Here's the ground. So that's 0.8 meters. Okay, so let's think about how I can fill the 9 kinematic variables here that I'm thinking about. There is 5 in X and 5 in Y, but the time is overlapping. So that means it's 9 variables. Let's see which ones I know, which ones I don't know. The X component of the displacement, I don't know, right? Because that's how far the balloon got from here to here. That's not given to me. So I don't know what that is. The X component of the initial velocity, well, maybe we could do this. Maybe we could do the displacement together, the initial velocity together, the final velocity together, and so on. So let's do that. The X component of the displacement, we don't know. The Y component of the displacement, we know, because we know that the balloon started here and ended down here. That's, or here. But if I'm looking at it from the back, so I'm just isolating the Y part, it looks like it started here and ended down here. So only if you're looking at the displacement as a vector, it looks something like this, right? It started at the green here and ended at the orange, right? And this is the X part of that displacement. So that's how far it moved horizontally. And this is how far it moved vertically. Now I know that this height is 0.8 meters because that's how far above the ground it is released. So my displacement in the Y direction then would be pointing from here to here. So it's pointing down at 0.8 meters. And we've agreed that anything that is pointing up, I'm going to call positive. So because it's pointing down, I'm going to call that negative 0.8 meters. See, it started up and ended down. So that means the displacement is pointing down at 0.8 meters, the vertical component of the displacement. The horizontal component of the displacement is pointing in the positive X direction, but I don't know how big that is. Okay, I don't really know it. Okay, what else? The initial velocity. Now the initial velocity, we agreed that the initial velocity was 6 meters per second in the horizontal direction. So if I was to draw the initial velocity, so this was just the displacement. If I was to draw the initial velocity vector, it's just 6 meters per second in the X direction. That means it has no Y component. It was just dropped. So that means it's 6 meters per second and it's pointing towards the right. I'm going to call that positive. And the Y direction, it was dropped. So there's no component to the velocity. If I threw it with some value, then I would have to think about this. The X and the Y components of the final velocity. Final means at the end of the segment here. So at point B, I have to think about that. Do I know anything about the velocity at the end here? Now at the end, you know, it's coming down like that. So it has some component to the velocity. So that's the velocity at B. It has some component in the X direction. And it has some component in the Y direction or the vertical direction, right? Because it was pulled down towards the ground. Now I don't know what these are because I'm not given anything about the velocity. Technically, I could take a good guess at what this is, and I'll show you how in a second. But as it is, I don't know anything about it. So I'm just going to leave this. I'm going to say I don't really know it. The acceleration. Now let's think about the acceleration vector. Just like we thought about the displacement vector and just like we thought about the initial velocity vector and the final velocity vector, now I want to think about the acceleration vector. What does the acceleration vector look like? Now, since this object is under the influence of gravity alone, which is something that maybe I should have mentioned explicitly in the problem, is that this is under the influence of gravity alone. So I'm not considering air resistance. I'm not considering any other forces acting on it. And since it's under the influence of gravity alone, that means it's experiencing an acceleration that is the acceleration of gravity, which is the acceleration that is pointing straight down at 9.8 meters per second squared. So this was the initial velocity vector. This was the displacement vector. The final velocity vector, I don't know. But the acceleration vector is definitely in this direction, right? It's g downwards. So since everything that is pointing up is called positive, so things that are pointing downward, I'm calling negative in the y direction. So this would be minus g, and g is negative, is 9.8 meters per second squared. Right? Now, because it's pointing straight downwards, that means it has no x part to the acceleration. It does not speed up or slow down in the x direction. Gravity is only pulling it down. It's not pulling it left or right. So that means it has no component in the x direction. It's all in the vertical part. Okay, what about the time? Well, the time information is the time between this event and that event, and I don't really know that. I'm not given what the time is. In fact, that's what I'm looking for in part A, the time it takes for the balloon to hit the ground. So that's really what I'm looking for here. And this time are exactly the same thing. They're referring to the same exact variable, which is the time between the beginning of the motion and the end of the motion. And that time interval, whether you're studying the x part of the motion or studying the y part of the motion, is the same time interval. So then you say, if I want to find the time, I can either use the x part of the motion or I can use the y part of the motion. That's the piece that is really important here when you're thinking about two-dimensional kinematics, is you're either thinking about the x part independently from the y part or the y part independently from the x part. Now, what's going to make the determination here is, first of all, the variable you're looking for, and secondly, whether you actually can solve the problem or not. So I want t, so that means I can use either x or y, but I look in the x direction and I find that I only have two variables. That's not enough. I need at least three variables in a kinematic story to be able to find the other two. Here I have three. I have delta y, I have initial velocity in y and the acceleration in y, so that means I can find the other two. So I'm going to use the y direction to find the time. And I'm going to look at the equation basically that doesn't have the final velocity in it because I don't know it, that I'm not looking for it at this point. So I'm just going to look for the equation that has delta y, v naught y, acceleration in y, and time. And that looks something like this. So to find the time, use delta y is equal to v naught y times t plus half the acceleration in the y direction times t squared. I'm looking for t, so I'm going to try to manipulate this equation to isolate t, and then I'm going to plug in the numbers. Now, because this is a quadratic equation, I can use the quadratic formula, which if you remember, t, which if you remember was something that looked like this. If y is equal to, or I should say, the quadratic equation happens when you think about ax squared plus bx plus c is equal to 0. Then you say x is equal to the story that you know, minus b plus or minus the square root and so on. However, here it's simpler than that because I recognize that the initial velocity is 0. So I can say this whole thing is 0 because 0 times anything will give me 0. So I can rewrite this equation as delta y is equal to half ay t squared. Right, but I want to isolate the time, so I'm going to multiply both sides by 2. So that gets rid of the half. And then I'm going to divide both sides by ay. So this means that ay is going to go down here. And then I'm going to take the square root to get rid of the square on the time. So I get the time is equal to, whenever I take the square root, the positive and the negative values are valid mathematically. But physically, which one of them makes more sense? When we're thinking about a time interval, it doesn't make sense to think about a negative time interval in this case. So we're going to think about the positive time interval, and I'm going to skip the negative answer here. I'm just going to think about the positive answer. And then I can plug in the number to find t. So I say that's the square root of twice delta y. Delta y was 0.8 meters negative. So that's twice negative 0.8 meters. Divided by the acceleration, and the acceleration was negative 9.8 meters per second squared. And I can figure this out. I can say that's the square root of 1.6 divided by 9.8. So What's that? That's probably something like 0.4, isn't it? Let me see. Let me see, let me put a calculator. So 1.6 divided by 9.8, that's 1.16. And when I take the square root of that, I get 0.4. Okay, so that's the time. I found the time. Now that's the time between the two events. So that's the time here. I can put that in here. That's the time, 0.4 seconds that I found. In part B, we're looking for the horizontal distance. Now, since I'm looking for something horizontal, that means I have to solve the X part because that's the horizontal piece. I want the horizontal distance covered by the balloon during its free fall from release to the moment it hits the ground. So again, I'm looking from this point to this point. I want to find this displacement here, this delta X. So that means I can study the same segment because I start from here and I end here. That's the segment I studied before. So let me study the same segment now. But this time I'm looking for the X pieces. Now I still have a problem because I still have only two variables here in the X direction. So in principle, I don't know how to think about delta X, except that we've said before that the time is the same time. So since I found the time to be 0.4 seconds, that's also, I can think about it from the horizontal perspective to be the same thing. So I'm looking for delta X, and I know what are the three variables. I know the initial velocity, the acceleration, and the time. I don't know the final velocity, so I can use the same equation that I used before for the Y, but now for delta X, I'll say V naught xt plus half the acceleration times the time squared. But this time the acceleration is what's zero, so this whole term goes away and I'm left with delta X is the velocity initial in X times the time. So that's 6 meters per second multiplied by the 4.4 seconds. So 6 times 0.4 would be 2.4 meters. So we'll take 2.4 meters in this side here. Okay. Now you can ask some more questions. You can ask, well, how fast is the balloon going just before it hits the ground? We can calculate that. It's not being asked, but let's do it as form of practice. So let's say for C, calculate the velocity of the balloon just before it hits the ground. And the velocity, of course, is a vector. So that means we're looking for magnitude and direction, or we're looking for X and Y components to describe it fully. So let's think about the X component since we already were thinking about that. So that means I'm looking for Vx. Now, since I know all four variables now other than Vx, then I can use any equation that has Vx in it because I know t and I know the acceleration. I just found the displacement. So I can really use any equation that has Vx in it to find Vx. So maybe I'll use this one here. Right, and we've agreed that the acceleration is zero. So that means that the final velocity is equal to the initial velocity is equal to 6 meters per second. And that actually turns out to be a feature of projectile motion because the acceleration is all in the vertical direction. There is no acceleration in the horizontal direction. So the velocity in the X direction stays the same. It does not change. And that's the reason why when you looked at the video from the top, you saw that the balloon was always under the hand because it was moving exactly with the same velocity that the car was moving with. So they were always in the same position as time passed by. And that's a feature that you can think about for projectile motion all the time because the acceleration is only in the Y direction, not in the X. So the velocity stays the same throughout the motion. What about the Y component of the velocity? Well, again, I can use the same equation because now I know everything in the Y direction except for the final velocity. Initially it was dropped, so there was nothing here, but the acceleration was given 9.8 meters per second squared times the time, which we found was 0.404 seconds. So we can plug that in and find what the final velocity is. So suppose I multiply this through and I get something like 0.2 times 0.4 is 0.08, let's say 0.1. So I get 4, I get something like 3.9, let's say 3.92 meters per second. Now the negative sign is really interesting here when you think about what this negative sign means. Let's draw this vector here. I have a vector here that I know 2 components of, and I want to think about its magnitude and its direction. So I draw it. I think, okay, this vector has a 6 component in the x direction. That's the vector that's called the final velocity. And it has 3.92 negative y. So negative means down when we're thinking about y, because we've agreed that up is positive. So this would be 3.92 in the downward direction. That's the velocity at the point B. And then the magnitude then would be the hypotenuse of that triangle. If you remember the vector piece that we just talked about. So this is called the velocity at point B. And it has this component is its x. And this component is its y with a negative sign. And this would be its magnitude. So we can find the magnitude and the direction. We can say the magnitude of the velocity at point B will be given by the Pythagorean, because this is a right angle triangle. So it'd be a squared plus b squared is equal to c squared. So this would be the square root of vx squared plus vy squared under the square root. So this would be the square root of 6 meters per second squared plus, now when I square the negative, is going to give me the same as if I square the positive, right? So I could put this as positive or negative in here. It really doesn't matter. It should give me the same answer. So I can figure out how big that is for the velocity. And if I want to know the direction of that vector, so let's say I want to know this angle here, then this angle I can think of as the tan inverse of the y divided by the x. Now the reason I'm putting the y here as positive instead of the negative that it was, because this negative here depends on the tools that you're using. It doesn't, its meaning is that it's pointing downwards relative. Its meaning literally means that it's opposite to the direction that you're calling positive. Because I'm calling up positive, that means that this would be downwards then. And in that sense, sometimes it confuses because the tan inverse doesn't know the difference between the tan inverse of negative a over b is the same as the tan inverse of a over negative b. So that's just a side. So it doesn't know whether you're thinking if the x is negative and the y is positive, or the x is positive and the y is negative. So the way I like to do is, just to avoid all of that confusion, is to draw it like this. To the right and down, we can always agree on to the right and down. Positive and negative, we can't always agree because some people are going to choose up to be positive, some people are going to choose down to be positive. So I'm going to draw it right to and down, and then I'm going to calculate it as if all of them were positive, find out what the angle is, and based on that, I can say the direction is that it's this amount of degrees below the horizon or the horizontal. So everybody can agree on that if you start from the horizontal like this and you go below the horizontal, then you can report this angle. And that's how you would report the magnitude and the direction of the final velocity. Okay, so we don't learn from experience, we learn from reflection on experience. You have to sit back and ask yourself, what do I know now that I didn't know when I started this problem? You have to summarize things for yourself, and you have to figure out what you've learned from going through